Okay, hello everyone, and welcome to another Hub Talk with Architects Hub Qatar. We're really happy to have you all here. My name is Sebastian Andraos, and I'm an architect student at Qatar University, and I'll be your host tonight. So today we'll be talking about 3D construction techniques with Mr. Sebastian Andraos. Thank you so much, Mr. Sebastian, for joining us today. Really glad and excited for having you in today's special talk. And moderating this talk will be Dr. Taryn Pakat. She's an assistant professor in my university, which is Qatar University of Architecture and Urban Planning. Dr. Taryn has a PhD Architecture and TRP from the University of Cape Town, Master's in Urban Geography from Stellenbosch University, and BTRP cum laude from Pretoria, South Africa. She holds numerous awards and experiences, scholarships, and is a member of the Golden Key International Honors Society and South African Planning Institute, and also the International Society of City and Regional Planners. She also has held the position of Deputy Director of Integrated Development Planning and Local Economic Development for a local municipality, and has a range of practical experience in strategic planning and urban design. Now, before we start, for those who are joining us for the first time, Hub Talks are hosted by the Architects Hub Qatar, a nonprofit association, architecture association that is all about professional networking through knowledge sharing. Please, you are all invited and welcome to share your thoughts and ask questions after the presentation. Of course, right now, this session is being recorded. We will upload it later on YouTube and Facebook. I'll also share some links in the chat. Please keep your microphones on mute throughout the presentation, but feel free to comment in the chat box in case you forget the questions after some time. After the presentation, the moderator, Dr. Taryn, will attend to your questions. And if you want to speak directly, please raise your hand. Please keep your comments or questions short and to the point so it can be easy to understand and allow others to engage. Thank you all for being here. And I will now pass my mic to Dr. Taryn.
Thanks, Shams, for introducing us. Good evening and welcome to all, especially to our guest speaker, Sebastian Andraos, who will be talking to us about 3D construction techniques. Sebastian is Vice President of Human-Machine Interactions at HAL Robotics, which he co-founded to ensure that flexible tools exist for architects and designers to gain access to automation. An architect by training, he shifted his focus to robotics in 2013. He specializes in computational linguistics and natural human-machine interfaces, developing interactive vocal programming interfaces and adaptive control of industrial manipulation. In this evening's talk, Sebastian will give us a brief introduction to the game-changing technologies inherent to construction automation and how they can be used in furthering the built environment. This presentation will last 30 minutes, and comments and questions are invited after the presentation. Please be reminded to keep your microphones on mute to avoid background noise pollution. I now give over to our presenter, Sebastian. Thanks, Sebastian.
Thank you, Taryn. Thank you, Shams. Thank you all actually for being here and inviting me, having me. As Taryn and Shams have both said, my name is Sebastian Andraos. I am a co-founder at HAL Robotics. And today I'm going to be talking to you about 3D construction techniques, in particular digital automation, which I'll explain shortly. So I'll start today just by briefly outlining what HAL Robotics do. I'm not going for some sales pitch, just so you know why I'm talking to you about this stuff. And then I'll really get into what digital automation is, why it's probably of interest to architects, engineers, and the rest of the construction industry. And then I'll go through quite a few case studies, because I think the best way to see what robots can do and what automation can do for construction is to see what robots and automation have already done in the construction industry. So without further ado, HAL Robotics are a robotic software company. We're based in London and Paris, and we produce software solutions to model, program, simulate, and control industrial applications involving robots and similar machines. We work all over the world and have clients just about, yeah, across the entire world. And we work in all sorts of industries, from arts and crafts through to R&D and education, and also in the construction industry. I personally used to work as an architect, so have vested interest in moving the construction industry forwards. And actually, this is only a subset of the industries that we do work in, but they all have the same kind of unique problem, which is that they are highly flexible, non-standardizable industries, and yet ones that also need a simplicity. They have non-expert users inside them. No one in the construction industry is going to spend 10 years learning how to use a robot and program it by hand. Same is true of arts and crafts. It's just too much of a burden. So they're really combined by this kind of duality of simplicity and flexibility, which normally don't go hand in hand, unfortunately, much as we'd love them to. So the workflow that we're going to talk about today, so that we're all kind of on the same page, is you've got something that you've designed, hopefully in 3D, in CAD, BIM, whatever it may be, and at the other end you've got a robot. You're not sure how to get the two together, how to get a robot to do what you do. So the first thing we're going to do is build a digital twin or a virtual robot. That's actually a bit more than the robot itself. It's all the fencing and structure, so we know that if the robot's going to hit anything whilst it's running. It's all the automation equipment, so the robot itself, any calibration tools, any external axes. I think we'll see those in use a little bit later. It's also the process equipment, so the tools, the gases, the material stocks, because a robot really is just a manipulator. It's we actually call them manipulators more often than robots in the field, and that's because all they do is move some tool around. If a robot's holding a welding torch, it's a welding robot. The same robot holding a saw is a sawing robot. They are highly flexible and don't really discriminate about what job they're actually doing. And then the last thing that needs to be included in our kind of virtual model is the controller or PLC or whatever it may be, the brain of the robot, the thing that's actually going to get it to do its job. And we pull all those together from various catalogs and start to make mechanical assemblies. But once that is in place, we need to actually decide what we want the robot to do. So we call that a procedure that the robot will execute. And we do that in a kind of fairly particular way at HAL Robotics, but the same is true of any automation tool. You basically tell the robot where to go in points around the space. We do it slightly differently in that we will take geometry, so anything from a CAD model, and we will create associative trajectories to that. So we will link a robot toolpath to, for example, in this little image here, to a hole in a plate. The reason we do that rather than saying go here, go here, go here, is that if you want to change where that hole is or the size of that hole, we'll automatically recompute where the robot goes. So as that geometry changes, you don't have to reprogram your robot or to compensate. So everything is associative and thereby parametric. Once we have that in place and we know what the robot's going to do, we can diagnose it. We can check that the robot can do what we want it to do. It's not going to crash. It's not going to collide with anything. It's not going to hit awkward robot issues like out of reaches or singularities. And once we've validated that, we can create this vendor agnostic program, which wraps up everything we want the robot to do in kind of a nice neat package. We can then simulate and make sure that the robot is going to do what we want it to. There's no sudden jump. We're not crashing. A visual inspection basically to make sure that we're doing the right thing and that everything's there. Check that we're hitting every hole that we expect to be hitting, for example, in this little demo. And then we can export that program to robot code. One of the banes of my job is that every robot manufacturer has their own language that you have to program their robots in. And so we try and abstract that support. So you don't have to write robot code for ABB or KUKA or whoever it may be. We generate that code automatically for you. Once you've got the code, it can be uploaded automatically to the robot. And because we have this connection to the robot, we can also read analytic data back off the robot and use that to either change our procedure or change actually the design of our parts all the way back at the beginning and kind of create this closed loop. Because we're talking about computers, in this case, controlling robots and programming robots, there's absolutely no reason that we can't have a single computer controlling lots of robots as well. And we are currently working on a tool called an orchestrator, which helps us to automatically assign jobs to different robots based on their availability, their capabilities, and things like that. So the benefits of this kind of workflow vary depending on who you are in the construction chain. Given that we're talking to architects tonight, for an architect in particular, what you get out of that workflow is the ability to know that your parts can be manufactured whilst you're designing them. You also get to control the processes that are used, which, as we'll see shortly, means you can actually push those processes probably beyond what you'd be able to do normally, and possibly even create something slightly different in terms of process, kind of a whole new process that may not have been possible before. And then because we're talking about that kind of flexibility and that automatic reprogramming, you can also design unique parts all the time and not be constrained by standardization and buying off-the-shelf components. So yeah, for me, there are three key advantages to this digital automation thing. And this project, which is by the Danish Institute of Technology, Sita, is a perfect example as far as I'm concerned. Not only is it beautiful, but it ticks all the right boxes in terms of technology as well. So the three advantages are that we are designing for robots from the beginning, that we can enable new processes by automating that programming, and that we have this ability to mass customize what we're doing. So the first thing the team at Sita did is use engineering optimization tools to optimize the panels of their bridge that they're designing. But beyond structural optimization, beyond the deflection that they're simulating here, they've also integrated into that manufacturing constraints. So can the robot actually make this panel is used in the optimization of the panel itself. So you're actually optimizing for manufacturing as well as optimizing for structures, performance, and the rest of your optimizations. They're then able to develop this entirely new process called, or entirely new, a fairly unique, novel process called sheet metal deformation, where you have a robot that basically presses on a piece of metal loads and loads and loads of times, slowly deforming it and pushing it into these 3D shapes. That's something you couldn't do previously. You could do it with the press and come down and kind of stamp things, but you couldn't do it with machinery because it's just too complicated to program. The only way to do this is with something that's generating the code for you. If I remember correctly, there are tens of thousands of lines of code behind every single panel that they're producing here. So it's unfeasible to even consider doing that by hand. And then the third, again, is related to the fact that we're generating code on the fly, and the robot and the computer don't care whether the code's the same as it was a minute ago or it's different. So we can create every single panel as a different, completely unique item based on its performance, based on the optimizations that we've already done. And yeah, and like I said, the robot just doesn't care. As long as it's a variation on a theme, we're not completely reinventing the wheel. Every single panel in this could be unique. I believe they're actually symmetrical, but it could be entirely unique. And at no real additional cost, which is kind of key. So I'm not going to go through a whole load of case studies because there's so much cool stuff that gets done with robots, automation, different processes, different materials. But to kind of structure it and hopefully to help you out if you start going through this process and start considering using automation in the future, if you're not already, of course. I like to break down the case studies and actually how you program a robot into three main groups. So the first is explicit programming. That's where you take some code, run it on the robot, and it'll just execute. The robot has no awareness of anything going on around it. The robot is purely dumb in this scenario, and there's no compensation at all. So this is generally used in things like 3D printers, where you've got an enclosed environment. The robot is itself the world, and so there's no risk of crashing. There's no risk of anything else. Same with CNC machines. The second step is adaptive. You start to connect fairly simple sensors to robots. Something that will detect where a part is that you need to go and pick up, for example, or something that will detect the distance to the table in front of it. And that data that's being fed back into the robot will allow it to adapt its trajectory. So you could, with this kind of programming, you could get a robot to always stay 100 millimeters above your table, even if the table is kind of wobbly, because it's reading that distance out of a sensor that's pointing downwards. And then we get onto the third and inherently the most complicated way of dealing with robots, and that's through collaborative. Generally, this is stuff where the human and robot need to work side by side and fully in concert, really, to make things work. And yeah, like I said, it's much more complicated to program than anything else, but is a requirement sometimes when you have tacit knowledge of a craftsman that is almost impossible to program into a robot. So let's start with the explicit side of things. This is a project one of my colleagues did actually coming on to a decade ago. It was to build a micro house out of hot wire cut foam. So here, all the panels are being generated out of a slightly variable shape. And then the robot goes around and cuts each of these panels out of a giant block. And what I really like about this is that we've got a tiny little robot with a giant block of foam. And actually, at the end of the day, what you get is this habitable structure. Okay, it's a foam vault rather than a real house, but it is orders of magnitude bigger than either the robot or the raw material. So you're really pushing the equipment and the materials beyond what you might be able to do if you had to leave that kind of margin of safety without being able to simulate what the robot could do. The same is true of this timber vault. So every single wooden beam in this, and actually every panel, is unique. They are all machined from standard pieces, and so the ends are exactly machined so that they slot together. Single screw holds them together, and I think that's been standing for a little while now. But yeah, so we're able to mix materials very easily. Similar process again. And this adding that extra level of complexity in that you've got two robots working together. Yeah. Then we can get onto things like 3D printing. So in this case, this is additive welding metal deposition. Joris Larman Lab, who then became MX3D, are the company who have just finished actually the 3 metal printed bridge over a river or a canal in Amsterdam, which looks amazing. If you haven't seen that, it's well worth looking up. And so in this process, all we're doing is welding a tiny bead of weld on top of another on top of another. But again, what we're talking about is extremely long paths. So every single probably 5 millimeters of this is another line of code that you would have to program by hand. So by being able to generate this code automatically, we're actually skipping a whole load of manual labor and actually facilitating these processes, or enabling them entirely. And then, of course, if we start to talk about 3D printing, we get into the concrete 3D printing world, which has been taking off quite a lot recently, and which we've been involved in for 6 odd years now. So, it starts with things like this wall project as part of the Democrat project in Paris. And that is, again, very similar processes. It's taking some intelligent piece of geometry, chopping it up into robot toolpaths, and then having a robot execute that. It can then be evolved into actually not printing concrete, but printing the molds for concrete. In this case, out of clay, which is therefore reusable. So once you've cast your concrete into those kind of tubes there, you can peel away the clay, chuck it back in a pot, mix it back up, and actually reprint it. So you have these reusable, highly flexible molds. Then geometry starts getting more complicated, and you can start to push the overhangs on the material. There's a lot of material science going on in this 3D concrete world, actually. And then things start to get bigger. So this is a real photograph of a school playground in Provence, I think, in South France. Which again, highly complicated shapes, optimized for its structural performance, and a really impressive feat of engineering, I think. This is another similar project, again, trying to work into the industrialization. So we're now kind of post R&D. So this is a project we worked on with Tarmac principally and Skanska, who are the kind of big contractors in this. And so again, just trying to draw that comparison between, we're making everything digitally first, and then the robots actually churning that out in the real world, and the scale of this stuff is big. So yeah, really interesting stuff as far as material science is concerned. And then Concreative, who are a company based in Dubai, who are now commercializing this kind of technology fully, and really pushing beyond what has previously been experimented with. And you can see here in the image on the right, this ability to play with the shape. So these kind of woven effect is actually not additional toolpath. It's the way that they've managed to overlap layers by actually, instead of having two layers set on top of each other, they offset them, so one goes in and the other one goes out, so the material falls down and creates this woven effect. So it's that ability to play with the process, push it beyond what should normally be possible, that I think is really exciting, and gives you that ability to experiment, and to take things beyond where they should be able to be. If we then come back to Sita, this is actually the precursor to A Bridge Too Far, which I showed you previously, and the process itself, as I said, is a robot pushing down on a piece of material a lot of times, and much more slowly than that video is playing out. But I like to finish with that as an example for explicit programming, because it really shows the problems. You're dealing with a material that's slightly unpredictable. It's a metal sheet, so it's got a little bit of spring in it. So when that springs back, you push much harder than you expect to, because the material isn't exactly where you think it's going to be. And so by pushing too hard more than once, in fact, lots and lots of times as you go around that material, you thin it out and you end up ripping. And so that's where things like adaptive programming come in. So there are times where you cannot get away with explicit programming, and you have to go to this next level of complexity. So in this case, it's as simple as putting a laser distance measure on the end of the tool and checking how far you are away from the material you are before you go and make that move. And so you can always guarantee that quality, because you're not pushing too hard on the material, because you know where that material is. Similarly, when you're dealing with other kind of heterogeneous materials like timber, you often need that level of adaptability. So in this is a steam bending of timber project. So all of these timber beams are steam bent. So they're steamed, they're then put in a vise, held by two robots, and bent into shape. The problem is that wood being wood, it doesn't go where you want it to go. So all of these silver markers on the wood in the photo in the middle are actually reflective balls that you would see in kind of movie studios to do motion capture. And those are seen by infrared cameras like the one on the left here. And we use that to update a model of exactly how the wood is being deformed, so that we can compare what's happening in the real wood to what the wood is supposed to look like based on our 3D model. And then we adapt the toolpath to add a bit of extra bend, a little bit less bends, to bend slightly more in a particular direction or twist slightly more in the other, to get that perfect finish. And so, yeah, it's a slow process because we're bending wood. But here, yeah, the robots are being adjusted in real time throughout the entirety of this bending process. And then we get on to collaborative. So again, this is where there is some tacit knowledge within the craftsman that really can't be passed on to a machine. So I really like this example of a glass artist we worked with in Taipei. He does these sculptures involving bent glass rods, and these kind of very geometric angular kinks are precise. Things need to kind of weave in the right places, so they have to be very precise. And until this moment, he was building a jig for every angle that he wanted to bend something to. So he'd have a rack of wooden jigs with a 15 degree, a 60 degree, a 17 degree, an 18 degree. He'd heat the glass up to the right temperature. He can see that with the glasses he's wearing. They present different colors according to temperature. And then he'd go over to the jig, bend it over, wait for it to cool, come back up, and then heat it up again. There's no way the robot is going to work out when the glass is hot enough. But a robot's really good at moving to different angles. So without needing a jig, the robot can move to 13.27 degrees, give or take 0.1 of a degree, and do that to a completely different angle every single time. So by combining the two, the glass artist gets to heat up the glass, know exactly when to make that bend, and then when he knows that's ready, he just kicks a foot pedal under his desk, and it triggers the robot to make its next move. And then it'll move down, he'll heat up the glass again, and they'll trigger. And so he's got this incredible flexibility all of a sudden, because he's no longer beholden to the jigs he's got available. And things are much quicker. He's got more control over the process, and he actually picks up the 3D tools needed to do this in the space of a day. So he was designing these toolpaths all on his own, which is great. We've then got things like vocal control, where you have this level of collaboration. So this is much younger than me, talking to a robot, asking it to pass me a brick, and with this camera system on board, it's working out where the brick is, going to pick it up, and then eventually would put it in my hand. We also have things we can do like teleoperation, where you're directly controlling a robot. So you can see my colleague here, Thibault, is moving his hand around, and the robot is tracking that and following it but only when it's open. So he has this fairly good control over the robot. We can then also expand that to lots of robots at the same time. Each of them can be controlled completely independently. So you could have multiple operators running multiple robots on a construction site or wherever it may be. And yet you can still retain this control over all the robots at the same time. If you need them all to stop or to reset, you can keep that control. We then start getting a bit more complicated. We can add gesture controlling. So Corey here just closed his left hand, and that closed the gripper. So he's beyond just motion. We're talking about actually activating and deactivating functions of the robot. So he can still move his right hand around to move the block, and he's keeping that left hand closed to keep a grip on the block that he's got there. Once we go a little bit beyond that sort of collaboration and teleoperation, we can actually also track any other objects. So we can have actual control being dictated by something that isn't a human intervention. In this case, It's just a hand moving these markers around, but those markers could equally be mounted on a part. So if you place that part in front of a robot, it'll locate it and work out what it needs to do without any kind of calibration. And as you can see, it's a very fine control. You can see if as the markers spin, you can actually see the end of the robot spinning as well. So you get this real, fine, fairly natural control over things. And similarly, we can start to read back data, as I said, off the machines. So this is a fairly basic welding process, but through which we're reading, the current of the welding torch, all the joint positions, and we can use that for kind of predictive maintenance, for understanding what went wrong. When something does go wrong, we can look back and go, oh, hold on a second, there was an undervoltage here. Maybe we need to look at why that happened. And then we can get even further and start to get into things like robots on construction sites. This was a demo we did a number of years ago now. There is a version 2 of this. So this was a robot to drill holes in concrete ceilings to then insert anchors and things. There is a version 2 which we completed trials of on a live site at the beginning of this year. I think we'll have videos going public in the next couple of weeks, but we're just a few weeks too early for me to be able to show you that, unfortunately. But I can assure you it's much neater and less covered in cables than this version. But I really think that's where we're eventually going, towards this on-site construction, robotics and automation. But I think we need to hit a lot of those other things on the way, and because it's so much easier to do. So yeah, I would implore you all to think about automation in your projects. Think about automation in your in potential production and manufacturing processes, but try and keep to the simple end of the spectrum for now. Thank you. I'm more than happy to take any questions.
Okay, wow, thank you, Sebastian. That was fascinating. What made you get into robotics? What sort of inspired you from being an architect to go into this amazing technology?
Frustration a little bit. I was working at All Design, and Marcus, who used to be my boss, is on the call, and I think presented to you all a few weeks ago. And we were designing pretty crazy stuff, and everything was unique. And it turns out that making unique objects is very expensive, very complicated, to the point that people would normally say no. So I went off and did a master's, kind of determined not to draw buildings for a couple of years because I was going to spend the rest of my life drawing buildings. And the university I went to had a robot. So I decided that was a great way to spend a couple of years playing. And actually started experimenting, writing precursors to the software we develop now, that allow me to automatically generate code for any part I could think of, basically. And so, yeah, I realized there was a potential use for that in construction, with my experience of having been so frustrated at not being able to get certain things built. And so the real issue we saw there was that the tools weren't available to allow people to do that. And so that's kind of why we started pushing this.
Oh no, that's amazing. Thank you so much for sharing. I'd like to invite questions and comments from the attendees via the chat room or verbally. If so, please raise your digital hand to speak. Please keep it to a minute or so that all questions can be entertained. Are there any questions?
Yes, Dr. Abdullah wants to ask. He's raising his hand.
Please go ahead.
Hi everybody. Thank you for your great lecture. My question: if you are using this in pouring the concrete in construction, how would you deduct a cavity like in a column or in a beam? If it's programmed to do certain procedure, cavity might not be part of this procedure. how will you detect that, or how will that affect the building if you detect it after the finish of the robot finish the whole work? Thank you.
So I think thank you very much. That's a great question. So it's all in, as you say, it's all in that ability to detect, if and have what you need in the procedure. So we develop tools ourselves to, for example, simplify concrete 3D printing. If we haven't foreseen the ability to leave a hole in what you want to do, then yeah, it won't track it. So it's really about having the right tool for the job. And if you've got a concrete pouring robot that isn't capable of detecting those cavities or leaving cavities and working around the formwork and stuff like that, then unfortunately I'd say that's not the right robot for the job. As I said, these are really flexible pieces of equipment that can be programmed in incountable ways with incountable tools attached to them. So it's really a question of making sure that they are programmed correctly, and the programs that are controlling them are fit for purpose.
Can I put the question in a different way? Let's say if you program it to everything, and unexpected manner happened, how would the robot detect that, especially if that manner can lead to failure? Like when I said cavity, it means column not taking the whole load. It might lead to a failure, might. But what I'm saying, if it's when we used to take computer, they teach us garbage in, garbage out. If you program garbage lead, then this is what you will get. So here it's the same. I mean, even if you put consider everything and something occur and due to nature, due to anything, high temperature, anything affect the programming, which is they took everything in consideration except that. How would you detect that? Is there like a second way of checking, or like in a normal procedure, a labor will do the construction, an engineer will come and check what's going on there and approve it or disapprove it. In this procedure, the robot will do the whole thing, or somebody else will come and check the robot's work?
You could do either, is the truth. You could, so the way we've operated on this construction site we were working on recently, we had the robot do its pass, and then we had someone come around and check that everything is correct after that. It's a question, I think, at some point of confidence as well. So once people are happy that the robot has done the right thing 100 times in a row, they're more likely to then go, okay, it's probably done the right thing this time. In terms of actually checking for errors, we have systems like watchdogs, which are external to the robot and would be checking that what the robot's doing is what the robot's supposed to be doing. So we can have all sorts of sensing systems to make sure that the robot is where it is. But again, it's an automated system that you have to put a bit of faith in. And it is, I think it comes down to that faith and testing things thoroughly. If there are unforeseen cases, I think it's about having something that can detect that the circumstances aren't normal. So if it's a question, as you said, of excessive heat somewhere, it would be up to the watchdog or up to some program running in the robot to check that the temperature is between some parameters that you want, or that anything it can detect is within this kind of usual working range. But it's complex. I'm not gonna hide that fact for sure.
Thank you. Can we organize a site visit to your site?
Unfortunately,
the Architects Hub.
Unfortunately, that's not my site anymore. It was a site in central London, which will probably be inhabited now. But to our offices, of course.
Thank you.
Right, thank you for the question. I saw Dr. Brian Sinclair, you were next.
Okay, thank you, Taryn, and thank you, Sebastian, for a fascinating presentation. I have a number of questions, but I'll just stick to one now, and then if time permits, we'll ask others. Just by way of my own background, I'm an architect and psychologist, and as pertains to this first question, I'm also a principal investigator on a $5 million project in Canada. I'm located in Canada, looking at quality in the built environment. One of the team members that we hired from London. She's a robotics expert, Alicia Vequez. But our project is considering quality as it's understood and defined and operationalized across Canada in all projects, private and public. And it's beyond aesthetics. So it's about experience, it's about formal, spatial, material aspects. So my question to you is, beyond things that would be obvious, like precision in tolerances or efficiencies in making, what do you see as a potential for robotics to improve the quality of architecture in the built environment?
It's a fascinating question. Thank you. I think there's a real potential for freedom in terms of what you're designing. This ability to create unique parts or apply unique processes that give things an additional quality that go beyond what you could buy off the shelf. I think really the concreative example that I showed a short while ago, where you've really got this woven effect coming through in the concrete, which is something you just couldn't do without the precision of programming and of the machine. It is the finesse required to actually get that effect through is something only a robot can achieve. So I think in that ability to push things forwards, push and experiment, and then make sure everything is fit for purpose, in that you're not constrained by standardization. So every part can be unique to give you that quality. I think is a potential way forward.
Okay, maybe I'll have a quick follow-up question before I turn it back. And I fully concur with you. Things looking at the concrete side of things, for example, and the mass customization is very fascinating. So another line of my research pertains to, it's more on the technical side, pertains to open building and agile architecture. And a number of doctoral students in my research group have been exploring agility or mutability as the new sustainability. The idea that buildings have to be able to morph and adapt and be taken apart and put back together based on really unpredictable and changing needs. So a lot of the examples I've seen, not just in your presentation, but in general, with regard to construction robotics and making using the robotics, looks at really quite static constructions. And I'm wondering whether you've thought about the ability for robotics to be deployed to create not only mass customization, but reusable, mutable, adaptable, sort of things that can be morphed. Because in a lot of ways, the idea of just building a static object that is on its place until it's ripped down is really sort of getting a bit thin. So what are your thoughts on that?
Sure. I think there are really two things spring to mind. The first is the ability for robots to add that level of, again, precision, because that's what they're best at, but to ensure that interfaces are interchangeable. So the fact that you have some beams that have a particular set of holes for bolts going through means that you can start to bolt things together, and therefore they are designed for manufacturing, assembly, and disassembly, and then potentially reuse into another building or into whatever else it might be. It could be that some of those interfaces are standardized to the point that actually they go and become part of a ship once you're done with those beams in your building. So I think for me that's probably the thing that springs to mind most. I have seen lots of projects looking at robots assembling and disassembling buildings automatically. From experience, that is complicated, to say the least. so I don't think that's a tomorrow thing. But maybe maybe the day after tomorrow, we could start to think about that.
Okay, thank you very much. If time permits later, I have more questions, but thank you very much, Sebastian.
Thanks.
All right, thank you. Ahmed, would you like to go ahead?
Yes, thank you for a nice presentation. Sir, in your opinion, how much we are using robotics in our construction projects in the world, and do you think and what prevent companies from using robotics in their projects? And the second part, do you think that using this or involving robots in our projects in the future will increase the cost of the project as well? Thank you.
So start on the first point. The short answer is not enough. There is not a lot of robotics and automation in the construction process. The reality is that there isn't that much difference between what goes on in, again, I'll take it as an easy example, but for example, manufacturing steel beams. There's not that much difference in manufacturing steel beams for a construction project compared to what would happen in shipbuilding, which is largely automated, or a lot of what would happen in the automotive industry. So I think there is a lot of low-hanging fruit in that regard. There are lots of things that could and should be automated more easily. I suspect what's holding the industry back as a whole is firstly education, the knowledge that that's there and it's available and it's not exclusive to these kind of super automated systems, and you don't need a production line to do that sort of thing. Particularly when it comes to construction, lots of things are small batches. You don't have this level of standardization which people assume is a requirement for automation. So you're not making 60,000 Mini Coopers. You're making this beam that's slightly different from this beam, that's slightly different from this beam. And I think people think that's incompatible with automation. So that to me is is really why there isn't more. And then in terms of cost, no, I don't think it will increase cost to projects. There's a very good reason that that car factories are all automated to a greater or lesser extent. There's actually a big push now to bring people back into car factories because there's a perfect balance between automation and manual intervention. And so by finding that, I mean, car factories aren't there to push the boundaries of what's possible with technology. They're there to make somebody a lot of money. So if it weren't financially viable and cost effective, I don't think that's what we would see. So I think in the short term, if it's something as like a unique selling point, there is a potential to up the cost because someone will charge a premium for that novelty and those kind of bragging rights that, we got a robot to do this. So we're going to charge you a bit extra so you can say that and put it in your marketing spiel. But no, I think in the long run, most robotics should be a reduction of cost.
Thank you, sir. Thank you for your answer and for nice presentation.
Thank you.
Fantastic, thank you. Marcos, would you like to go ahead?
Hi, Seb. Yeah, great. It's always funny seeing you like this. Yeah, really enjoyed that. It's amazing what you guys are doing, and it's been quite fun just seeing that progress. So my question goes to what you said earlier about when you worked with us before and sort of getting frustrated. So how far off do you actually think from what we're doing, actually about 8 years ago now, to actually on a mass scale being able to do the things that we're doing with the economies of scale that is needed to make it efficient?
Yeah, I mean, I think we're still further off than I'd like us to be. as as the construction industry in a whole. Like I said, there's lots of low-hanging fruit that could and should be automated, but people are reticent to do it because they've never seen it done before. So there's a real leap of faith into that. There is a capital expenditure associated, but I think things are starting to get there. I mean, I think all design is a great example of pushing the boundaries of what's possible. And apologies for making references to things that people may not all know, but there's a particular building that All Design finished recently in central London, or in northeast London, called the Neuron Pods, and it is pretty crazy looking metal tube shaped kind of blob. I think in terms of the way that was built was actually with shipbuilders, and I think that's kind of indicative that the construction industry has a lot to learn from these other kind of parallel industries, and I think once that ball gets going, and I think it's starting to get there, we're starting to see big investment from companies like Skanska, Laing O'Rourke into automation. I think once that gets going, it'll start to snowball, and it's really a question of these smaller manufacturers seeing that things can be done, have been done, their peers, their competitors even are doing it, and therefore they probably need to jump on the bandwagon. And I think it's a win-win in that scenario. We've worked with steel fabricators before who have been really nervous about trying this sort of stuff out. We helped them reduce the cost of testing, and they're now deploying machines all over the place. And their competitors, their neighbors actually, because it's all very, very localized, are kind of freaking out and trying to do the same. So I think it's it will grow exponentially once it reaches that kind of critical mass. But I reckon in the next few years we'll see a real explosion.
Cool, thanks, Ed.
Thanks.
Fantastic, thank you. Brian, there is a bit of time. Would you have another question that you would like to pose at this time?
Sure, yeah, thank you very much, Taryn. So the next question pertains to sort of what I think is typically a conservative deployment of emerging technology. And I think, for example, of the arrival of CAD and AutoCAD in particular, and more recently, maybe some of the software rendering engines. But looking at AutoCAD, there was a whole period when it just arrived where architects and students of architecture were really designing to the capacities and capabilities of the available software. So maybe the first part of this question is, do you see a parallel in robotics whereby there's maybe a conservative posturing, or based on the skills of the coder or the hardware, the software? Is there this first step out that is really maybe quite conservative, and where designers are working to what they know are the available capabilities and capacities?
I think there is, to an extent. It's one of the things that frustrates me, knowing people designing to the capabilities of some digital tool, because either they don't know how to push it further and use it properly, or because the tool itself is insufficient. But there is a limitation to that, in that if you're programming things by hand in particular, or manually clicking everywhere you need a robot to go, you can't do very complicated things. There are only so many clicks you can do in a day, and then things take too long, and therefore they become prohibitively expensive because somebody spent 6 months clicking everywhere that they need a robot to go, and then you change the design slightly and they have to start all over again. So I think actually, particularly in construction, there isn't that problem because people just won't do it. It's something that we're trying to change entirely. It's making the cost of flexible automation as low as possible, so that we're not limited by what a robot can do, because actually all the robot's doing is moving around. The rest is all process based. So, and I think that's something actually that's worth picking up on and kind of doubling down on. The process itself is considerably more complex than getting a robot to do certain things nowadays. So actually, how do you weld? How do you make sure that your pieces are in exactly the right place to weld? What kind of concrete you're using to 3D print your concrete? There's a whole load of material science. What kind of pump? How do you avoid your concrete setting in the tubing? And then you have to, from experience, you have to get a giant mallet and smash out the concrete from your tube because it all set in your ductwork. So yeah, I think it's, there's a lot of complexity in the process, and I think the right tools are the ones that don't create those limitations.
Okay, maybe just a quick follow-up question, putting on my educator's hat. So I teach a lot of studios at my school here in Canada. And, when laser printers or the 3D printers came out, there was a relatively slow adoption, but now they're commonplace in studio. We at my school have quite a number of robotics, and we have professors teaching robotics, but it's not yet a part of the studio. It's very much separate coding classes. They'll spend a semester, and at the end of the semester, they get the robot to line up a set of to basically, without mortar, just dry lay a series of bricks, or the robot to write something on a whiteboard, for example. So there's no real implication whatsoever yet in studio. So do you see schools and do you see education that are really beginning to blend in a pedagogical sense the capability of robotics and the preparation of future architects?
Yes, we are the technology provider to a lot of universities, a lot. And so, I mean, that in itself to me is a good sign. Many of them are architectural schools because that's where we have kind of good connections. And what is being produced definitely goes beyond the kind of stacking of bricks into, the stuff we saw from Sita, for example. In fact, a lot of the projects I've shown you today are actually academic. We don't normally get to show stuff we do for commercial partners, unfortunately. So yeah, there is this real push. It tends at the moment to be more dedicated research. I think there's a kind of, there are a few. I mean, where I went to university to do my master's, for example, we had there was a tight link. Our studio space had a robot in it, so there was no really getting around that. And I know there are the universities around that are starting to blend that that thing.
Yeah, and I certainly see the progress on the researcher side, the integration in studio and the students actually doing meaningful work. I guess that's what I'm concerned about, is the slowness of that to arrive, but it will arrive, of course, but it's just
everything trickles down eventually. I think there's has to be a certain drive from the students, which triggers things quite a lot. So I know, for example, at Malakir, where I did my master's, the only reason there was a robot is because there was one particular tutor and one student who were all over it and were pushing the university to get a robot. So yeah, it takes a particular drive from a small number of people generally, because once that was there, the university then goes, oh, we've got all this equipment, we better make the most of it. So let's get loads of people to use it.
Certainly the students are keen. They're big drivers of this equation. So yeah. So I think it's the opportunities that you get whilst you're at university are unbelievable. So and that freedom to not have to actually worry about reality. Well, thank you very much, Sebastian.
No worries. Thank you.
Great. Thank you very much. Are there any more questions?
Marcus is raising his hand.
Thank you, Shams. Marcus, would you like to go ahead?
No, I forgot to take my hand down. Sorry, always do that.
Okay, great. Thank you very much then for a wonderful session. Thank you, Sebastian, and thank you for those who attended. I'd like to pass the session on to the host for closing.
Yes. Okay, so thank you so much, Mr. Sebastian, for educating us on this important talk about 3D construction. Thank you so much, Dr. Tan, for moderating today's talk. Thank you all for attending this special talk. And I will now post an email in the chat. For the members of the Architects Hub Qatar attending today, please, you can email us if you want to receive your attendance certificates. Send this email to admin@architectshub.com. If you're not a member and you want to join, send us a message on the same email I just posted. We will send you an invitation to join. I'll give you 10 seconds to copy or screenshot it. And yeah, so goodbye now. Wish you all well. I hope to see you again in the next week. And this was so fun and interesting. Thank you all so much. Bye.
Thank you, everyone.
Thank you. Thank you, Mr. Sebastian.
Goodbye, everybody. Bye.